Hello, Ross Finlayson. It's December 27th, 2023. Welcome to another talk on moment and motion. As the sound of the train horn in the background carries to us, it's a northbound train going through Seattle, which has a tunnel under it, and is one of the main passages north and south through here, points north and points south. So in terms of moment and motion, I imagine it's a giant diesel locomotive, maybe a couple. The tracks are standard gauge or American gauge, and the cars range from 20 in a small train to sometimes hundreds of cars in the larger trains. So in terms of multimodal freight, roll on, roll off, rail, water, and road and air. It's one of the greater reasons why technology became so important to industry, as the first in America, the rail lines and the Transcontinental Railroad, and then what later became the interstate highway system. Those being the primary investments in infrastructure that made commerce possible. So today, what I thought I'd talk about was moment and motion. Looking here at these collected stacks of books, there's Galileo, one of our inspirations, and the stories for him, and not only the received wisdom, the formula, and this is the derivation you must sit and follow because it is declarative, and you must be able to recall and produce it because it's required later, it's prerequisite of the theory, and what's gathered in later theories that are those things. Then also he has his role as a model of a guy who was then as so involved in the affairs of the world, and as to why it's not just a school of a man, but a study of a man. So Galileo is pretty cool, and he's famous for his works in physics, and that's why he's mentioned today, not for anything else. Then the other stuff just kind of comes along as with it. Waves. We're studying waves because the wave formalism is very de rigueur. It's very usual. It's very practical. It's very commonplace. It's kind of ubiquitous in terms of the notions of the traveling of things and the radiation of things and the way things act and operate. Besides, kind of like current, for example, as identified with a circuit and Ohm law, Kirchhoff law, which you'd be familiar with, is for passive and active components electrically in a circuit. And as with regards to other notions that are of the closed systems, that the wave is basically propagation in an open system. It reaches and ripples and reflects off its bounds. That the wave is thus a reflection upon our open and closed metaphors of systems, and that the open and closed systems basically identify the boundaries of invariance. That an invariant determines that there is a strict ratio, here 1-to-1, and then that establishes what are symmetries. Then we have a theorem called Noether's theorem for Emmy Noether, a scientist of the early 20th century, who established that for any symmetry there's a conservation law, which is here as of just this balance of things, and so it's pretty straightforward to consider how that is, and then the idea here also is what that really entails is a continuum law, because as we get up and outside the linear and out into the super and then into the all the fields of potential vis-a-vis the classical impulse and its reflection in the potential, is that that's quite the open system vis-a-vis how we attach these moments to actions and events in the classical, vis-a-vis motion as generally indicating a rate of change with regard to any kind of rate of change, but here mostly in terms of motion in space. So the waves are just a really usual thing. Now, do I use wave physics and its formulaic mechanisms regularly? Is it my milieu? Is it kind of my mental scratch pad of the objects of the elements? No, not really. My trade is that I'm a computer programmer. I'm a software developer, and I have been for a while, say 15 or 20 years or more. And what I do is I'm a salaryman, and I work for a capital industry in the aerospace sector. And so I'm not, although I'm involved in computers and the internet and all these kinds of things that are involved with standards and specifications, is arrived from the IETF and the W3C and what would be and da-dee-da and all the standards and these kinds of things, is that it's not at all associated with things like the gig economy, social platforms, or mass marketing of the retail sort, or spyware, or anything else to do with what are considered valueless offerings of the tech industry. I work in a capital industry, and so I just swing a wrench in a sector, and I kind of have the responsibility to keep the lights on for a system of documents. So in that sense, of what I've studied for 15 or 20 years is all of such matters of computer engineering and software engineering, which is easier than computer engineering and electrical engineering. The most I worked in electrical engineering proper was at a chip place, a fabless semiconductor, who designed chips, but they don't actually operate the fabrication or the fab themselves, the fabrication of the chip. And so what that was involved with was a codec, compressor, decompressor, for a specification called JPEG 2000, Joint Photographic Experts Group, Standard 2, JPEG 2000, where you kind of have JPEG, which is very familiar as the most usual, successful, and ubiquitous continuous stone image format everywhere. And vis-a-vis that there was JPEG LS then for a lossless profile for JPEG. And then that JPEG 2000 introduced going from the discrete cosine transform in Friends, and then the entropy coding to the wavelet transform in Friends, discrete and forward and inverse wavelet transforms. With regards to time and frequency, in terms of the color space of usually tristimulus color space models like red, green, blue, YCBCR, LUV, these kinds of things, ABC, after the CIE, the Committee International D'éclairage, a French plan in the 1920s, established some standards for what are names and how to evaluate things that live in the tristimulus color space of color. So optical light in its emission and reflection and absorption and then in the intromissive interaction of it with the rods and cones of the eye and the back of the retina is largely known, or with the charge couple device, the CCD, have that there are color spaces. And these are the models of how to arrive at for a given hue, intensity, and brightness, or as from a palette and the gamut of mixing additive and subtractive colors, of the primary colors, the color wheel, and all these other kinds of concepts where they live in kind of a tristimulus color space, kind of like water's boiling and freezing lives at the triple points of boiling and freezing according to temperature and pressure. So light is not so dissimilar. In a sense, we kind of heard about this in the last time when there was talk about the hydrogen line and why spectrometry was so relevant and important for the development of all the theory and the practice of what makes many modern marvels of technological capability possible. And so for the hydrogen line, then there's a sodium line, and so there are low pressure sodium lamps, and they emit one wavelength. And then there are high pressure sodium lamps, and they emit more. They emit more of the spectrum, the diffuse, or insofar as how it goes, that it starts to show that there's this harmonic and the reproduction of overtone and these things that result resonances that make it for so as to why when we talk about what is red, green, blue, and for our usual spectrum, red from the infrared, orange, yellow, green, blue, indigo, violet to the ultraviolet, in terms of lower frequency and higher frequency, these optical visible light vis-a-vis electromagnetic radiation, which is modeled in the same way as in terms of the propagation of the waves, which is in the electrical field and with charge and massive particles so reflected instead of the this field of space where light travels unimpeded according to the L principle at a constant rate through the space where it's in, locally, of course. That special relativity is our piece of theory that governs light's travel, and these days is what's called local, and relativity of simultaneity is non-local, because really the general theory of relativity governs what's in space, and according to space and time, what makes space contraction, which is time dilation and length contraction together, space contraction. And that otherwise it's usual underpinning the theory according to Einstein in Out of My Later Years, his book, which is his final theory and his word on it. So I studied computers a lot, and I studied the internals and the formats and the specifications of all these type of things. And with regards to that, a computer is a tool, and it provides sort of a lever in terms of moving mountains of moles in terms of bits. It's all zeros and ones down there. It's kind of true and false in the middle, and it's things up here, objects in a usual sense. With regards to facility, is something like database, the file system, the message queue, web services. All in nodes, live in a fleet, all have names, according to build time coverage and runtime coverage, what's called full stack, full life cycle, all phases software development, which I like to think of as a waterfall and design build, and that these days is pretty much broken down into usually more easily digested bits for everybody in terms of a usual setting like a enterprise corporate IT environment. So that's what I know. And I'm not a practicing physicist. I'm not a practicing chemist or along these lines. And then I have a mathematics degree, and I study mathematics. And so this just give you an idea that a usual lay person in the laity of it, not like the cult or whatever you want to call it, of science and big science, can learn a lot, and especially when it helps coordinate what's their intuition with what's the fundamentals and the elementary and the foundations, which arrive at that then we can talk about the things which make a kind of a sphere of knowledge, a totality, vis-a-vis that there is a theory at all, we are in it, and that it's true. So with regards to that, what I'd studied after and before I got my mathematics degree, I wanted to study continuity and the theory of why it was so. And so when you study these things, then you'll learn about modern mathematics and what's standard and what's regular and what's ordinary and what's non-standard and what's extraordinary vis-a-vis completions and limits, what make for the usual approach to what are completions as extra the inductive, or as when Zeno's arrow arrives. One time I was talking to one of my uncles, and I explained to him my concept of Zeno's paradox. And, he was a calc teacher and a chemistry teacher, instructor, for like the advanced placement in high school, for 10 or 15 years. Before that, he was practicing chemical engineer for 15 or 20 years. In my childhood, there were several times they sent me good books that were enriching, and in with regards to mathematics, and they helped. I felt they opened my world to a wider horizon. Besides that, the curriculum I had was good, and these kinds of things. So, anyways, I told him this about Zeno. He's like, "You've broken the speed of light." And I was like, "Oh, really?" He's like, "Well, yeah, because it's kind of this sense of like you can never outpace yourself, and this and that or whatever." But it was a positive thing, and so I was pretty proud of that. One time I was sitting around the dinner table after school in school, and so my three brothers and my mother, father, our family, we all sat at the table and ate dinner every day. It's about the same time. And every day, and so I said, there are 4 dimensions. There's 3 space dimensions and 1 dimension of time, and everybody got it. I was like, So these are the kinds of things that speak of enrichment, on the interpersonal level, and the sense that it's like it's the whole world of things is out there. The whole world of things is out there for people to find. The internet became this tremendous library full of all these funiculars to who knows what, ad mobs and all this kind of stuff. Their goal is to sell your attention by taking it from you as cheap as they can. And it's not my goal or role to say that that's right or wrong, because que sera sera kind of a thing. But there are definitely authorities and better sources for anything that's really truly a matters of learning and is of value, and is not just what we used to call pulp. Pulp being a very cheap form of paper upon which things were published that weren't going to last very long. So anyways, then with regards to the authorities, you can usually just go to Wikipedia, and it's usually good. It's usually solid. It's usually well reviewed and established, and it's pretty clear. Compared to anything else, if it's got an ad on it, it is not the source. So, let's see here. Owns the frequency, the wave number, profile, period, the wavelength, properties of a sinusoidal wave with the properties that it's got 2 phases in and out, or is a range between 0 and 2 pi. Talked about the exponential form. Here the author gets into what are called progressive waves in 1 dimension, 2 dimension, and 3 dimensions. So he defines a d squared phi over dx squared partially equals 1 over c squared of d squared phi over dt squared. So the key separation of the components of x position and t time is really usual in a lot of things with regards to otherwise the separation of components. Like any kind of these transforms used in the continuous tone imagery for its compression, for the extracting of its components that are most significant in terms of getting the kind of the primary principal part of the value out of that, or is that these ideas of the Eulerian and Gaussian are similar about that in terms of what they attain to and how it's so arrived at. That here this expression in the differential helps express that this form encloses that then what will so proceed and as to go out of that is according to what we've been talking about, the Laplacian. That the Laplacian, when that equals 0, is harmonics. So that today the theory of potentials is largely a study of harmonics. So these are the kinds of things that get into these waves. And then so for 2 dimensions, it's just a sum of those. D squared phi over dx squared plus d squared phi over dy squared equals 1 over c squared d squared phi over dt squared. It's the Laplacian. And when it equals 0, then it's a simple thing as part of a singularity, the envelope with regards to how it can be kind of considered. So when you get into some of these shapes and forms, and sometimes when things go up higher in dimensions, and with regards to how they go, then it results that still the inner product exists and can be withdrawn as a piece. At other times, there's combinatorial explosion. When things rise in the dimensions, then it so arises that their detail explodes in terms of combinatorial enumeration. To go through the process of giving each of the possible combinations a name, and that they need to have as much space as they need to fill the space, is exactly as so for algorithmics, which is the study of algorithms and data structures, and the resources that they require, or particularly it's what's usually the worst case that they will require in terms of something that's then can just be left alone as simply understood vis-a-vis adaptive algorithms and the optimal conditions and these kinds of things, which can arrive as from varied in many means according to the distribution of the data and what's in it. So formulas are data and numbers are data, and it ends up working out that a lot of these objects in the field that we have formally then they could be implemented as automata, automatons, automata. So the formal automata are classes of machines, logically, and we normally think of that in terms of finite state machines. Finite state machine is a machine in the sense that its machinations result that it's orderly in this way. So a finite state machine, or FSM, has got a start state, any number of end states, and any states in the middle, and transitions between those according to events at any given state. So the finite state machine is one of the most usual fundamental concepts from formal methods, which includes formal automata. As with regards to the most usual sort of function that's a formal automaton, the acceptor function or the rejector function. The acceptor function given input returns true or not. The rejector function given input returns false or not. Together, you can say that a function that's both acceptor and rejector returns true or false, one or the other. These are defined in terms of formal languages. Then in terms of the complexity of classes of those, it arrives at for a machine in its given state as the numerical methods, because then how all this stuff gets computed is crunching the numbers, that for these computer algebra systems, they work pretty much directly on the same sorts of terms we have elementarily. And then that the idea with the numerical methods is that, well, at some point we give up trying to be perfect and say that then this algorithm will start computing and get very close, find the principal components and get this sort of thing out, and result in engineering cases. So it's all one thing. As with regards to the computational realm of the abstract symbolic logically, and also the numerical resources and the finite resources, the large and unbounded, basically finite resources of a computer system. So let's see here. 2 dimensions. So he reads off further that in 1 dimension that is read here kind of in the Laplacian form, as it were, in a sense. Phi equals f of x minus ct, which we're familiar with, plus g of x plus ct. So here it's with regards to this in and out of phase, and that it's so defined that then this is parametrically what he gives is as the form of an equation, this progressive wave, or is it a traveling wave? We'd be discussing it as of then. Then in 2 dimensions, phi is just given in a similar parametric form, f plus g, f of lx plus my minus ct, of g of lx plus my plus ct, where L squared plus M squared equals 1. So here he's employing the roots of unity, which must, or does, have some relation to the Eulerian and Gaussian Euler's identity, meaning all the derivations that follow back down from that, and then we bring it back in from that. They have all the complex numbers back to the real parts. With regards to the x squared plus y squared equals 1 as the most simple and well understood parametric form for a circle. And so that, and all the roots of unity live on the unit circle. The complex roots of unity. 3 dimensions. same. It adds another one. And then it gives phi equals f of lx plus my plus nz minus ct equals g of lx plus my plus nz plus ct, opposite sign. The L squared plus m squared plus n squared equals 1. Now the problem when you get to the higher dimensions is that the parametric formula for a surface like so, the spheroid or the ball or the hypersphere is kind of the same. But that free rotation of the plane gets involved with the affine and the gimbal, notion of the gimbal, kind of like the gyroscope we were looking at the other day, and with regards to its interlocking the moments of the arms, their concentric rings, and a given particular configuration may be astably resistant to a given otherwise its precession, and it tips over. The gyroscope does not tip over, but it does. Gimbal lock. 3 dimensions spherical symmetry. So, then stationary waves are given as the same formula for the one-dimensional case, and then phi equals cosine px sine cpt, or phi equals e to the plus minus px e to the plus minus cpt. So that's as with regards to the period and the number, and then the sine and cosine, they're complementary functions, or the exponential, the product of those is out of those. So these get into with parametric forms. Parametric forms are, they're formulas and they have variables, they're called parameters. So now this is basically the statement of outlook that if you can find anything that so attains to and makes these formulas, they are of a kind. In computer science, you might say duck typing, because computer science has what's called the rich theory of strong types after C.S. Peirce and Bertrand Russell, and the theory of types, Kokand, Lewin, Peirce, North Holland, theory of types, and then the idea of a loose theory of types is for extensionality is like if it walks like a duck and it quacks like a duck, it's a duck. So duck typing is basically just with regards to a loose sort of a association. But here with anything that is just going to be so associated and to model, this is exactly what a model is in model theory, to model these things, it is one. It is by what it is. It does. For what they are and do. The most usual notion of declaration of shared logic or shared associativity of common behavior of objects in computer science is a something else by its type, or has something else by its type. Like bipeds have feet, they have 2 feet. Cows are animals and dogs are animals. Cows are not dogs. Is and has are the most usual things. Then it's arranged in kind of a hierarchy of a directed acyclic graph, what's called a tree data structure, which has a root and branches and it always grows one way, directed acyclic graph. And then the idea of that, well, those relations also invert the diamond. It's called inverting the diamond. So then you have what's called things like when you have multiple inheritance, you got double diamond, and then when you kind of figure out how to talk about when things more primarily are from the leaf than the root, inverting the diamond, which is it's not very much usual practice because normally everything is just kind of laid out simply in terms of its state at rest, a data item. It should be noted that there are exponential modifications of all the above equations. In solving problems, we shall more often require progressive type solutions in cases where the variables x, y, z are allowed an infinite range of values, and stationary type solutions when they're allowed range is finite. So this kind of helps express the thing that kind of like the difference between the pendulum and the spring. For the pendulum, you should look to Hooke's law. in the time of Newton and around is that Hooke's law establishes a very simple linearization and simplification that later is you find all over physics because it's part of Cavendish and Hooke and all that kind of stuff. The normalization of things vis-a-vis, well, first it's denormalized to result that you normalize that vis-a-vis the infinite well and the pendulum, the finite well and the spring. So then he starts talking about some descriptive forms associated with waves, friction, damping, and here he's described in terms of this being dissipative forces. So we have the attenuative and dissipative are just kind of these concepts that help carry along that this coefficient like so will result, it trails out to like so. That's the way it is. Most of the waves with which we shall be concerned in later chapters will be harmonic. Not all are. The notions of tone and overtone in the harmonics have that constructive and destructive interference can be also in waves. So, and that there's arbitrarily contrived the fractal waves. The fractal is the infinitely repeatingly smaller and smaller self-similar, yet not just trivial, or not necessarily just trivial, is vis-a-vis the fractal. When we were kids and computer graphics started being a thing, anti-aliasing effects are when you draw a line on the screen but it is not smooth, it kind of has what's called jaggies, anti-aliasing effects or jaggies. We call those fractals. They're the same all the way down. So it's otherwise though a theory of the self-similar in increasing resolution and scale. The complex quantity is itself a solution of the equation of wave motion, as can easily be seen by substitution, and consequently both its real and imaginary parts are also solutions. One way. In such a case, the apparent amplitude A is usually complex, and since big A equals A to the E to the minus I epsilon, we can say the absolute value, or the length of the vector so defined by A, the root of the sum of the squares of the pieces, is the true amplitude, and negative arg A is the true phase. When we get it, when I started learning about root mean square, I could see it was in all these tables and it was in all the specifications, the parameters, the components. I still don't know really what it is, root mean square. But what it is an expression that power washes out, but it still kind of goes flat, or when it goes as of a current, in terms of that, then when it ramps up and backs up, it's like, here's what will result. It's kind of like a wide model as of a flow of things. Then with regards to that, it's a little bit, because the electricity is the opposite of liquids in its fluid model and how things flow, the skin effect, core effect. Otherwise, that they have the same kind of model, just like voltage is potential differences, electromotive force is just like the height of the head of a drop of water in a pipe or openly with regards to the potential energy that so carries with it. So where models are the same is like, this is duct typing, they are the same, and it's like this is a duck that flies and this is a duck that swims. All right, except that one flies in electricity and the other swims in water. So it's kind of like that. I just made that up, but I never heard it before. So. For instance, in 3 dimensions, phi equals big A times e to the 2 pi I in this quantity, nt minus this inner quantity, px plus qi plus rz, would represent our harmonic wave with amplitude big A moving with velocity n over root p squared plus q squared plus r squared. in the direction xyz equals PQR, the proportionality. So this sort of geometric interpretation helps a lot, because otherwise it's not having a geometric interpretation of things that once frees the mind. It frees it to say, I am free to just only deal with these tractable quantities and stay within this abstract symbolic realm of the pure part of this mathematics, this pure part of the mathematics. Whereas with the geometric attachment, you can say, as furthermore, I can associate it back to the more of the mathematics. That the entire thing of mathematics is called pure mathematics, and anything you do with it is called applied. And then when it's formally, is symbolically a model only of mathematical objects, that's called the pure side of it, the pure mathematics part. And anything that's related to is the applied. And how you do it is the applied. Because it has any way it can go. You can, if you establish it's all everything one way, that's kind of the goal of the entirety of, we really want a Hilbert program to explain all of mathematics as itself. And that's how it could be kind of considered. Owns, waves. Note that this is not a single valued function unless we put restrictions upon the allowed range of phi. Theta. All right, so that's some looking at this here as we're carrying forward waves on strings. So this the first or the first recorded sort of school of a theory for practical application is sounds by the length of strings, and so the resonant frequencies, which so arrive according to the thickness and the length of the strings, as for stringed instruments in musical instruments, with regards to the octaves with which in their 8 notes in the usual octave scale are so reflected that the frequency of a note and the frequency of the next octave is a doubling relation. One is just twice the next one. And it's very natural to hear such tones and relate them exactly like so as increments and decrements by the orders of magnitude. Exactly why it's so great to have addition formula for exponents in terms of their powers, taking their product and summing their powers, and you get computed the sum of the powers is the power of the product. Addition formula, doubling, a doubling space, a halving space, angle of doubling, frequency doubling. All right, this is much to be explored. Waves and membranes, surfaces, flags, longitudinal waves in bars and springs. So here we're getting into springs and their relation to the rigid part, it's incompressible, the spring that's compressible, and it's also restitutive. It returns to the form with which it was at before it is disturbed, deformed, or displaced. It's restitutive. Is vis-a-vis it's the properties of metal, ductility, malleability, and these kinds of things. With regards to whether malleability is just deformability, but ductility is whether you can actually just hammer it out and it will form something, no matter how thin it is, it will stay. These are properties of metals, and usually only metals. Metals are particular kind of elements with regards to colors and metals. And so it starts to define how things can make. You can make a configuration of things, and they have a configuration space, and they go together. So there's still much more reading in this book to get to with regards to. Here's section 88, general considerations. The discussion of the last paragraph related to the case of plane waves, falling normally on an aperture whose size, while large compared with the wavelength, was still small compared to the distance from the aperture to the screen on which the pattern was being observed. We might refer to this as diffraction at a pinhole. The camera obscura is usual a notion of this, that the camera obscura happens to make because of optical lensing, the optical effect of light, that though it does no lensing itself on its own, that will the image so conveyed stays organized because only the organized image is what's left. So then it arrives projected upside down on an interior wall. And another thing that to consider with that is with respect to nonlinear called the near field, the far field. So the near field is basically the idea is like, this is what it's like locally, and the far field is like, this is what it's like far away, and when they're the same or when they're different. But the equations arise in another far more important way, which we must now explain, which is known as Fraunhofer diffraction. Consider a plane wave shown as A prime in the diagram falling normally on a convergent lens L. L replaces the previous pinhole. This lens will convert the plane wave into a spherical wave which converges at Z, the focus. On account of the finite size of the lens, the focus is not perfect, and we ask the question, what will be the intensity interpreted at point P at the focal plane through Z? And it shows the converging wavefront as through the lens, then that it has an incident wavefront. So it's kind of like a matter of projection. And here in some of the other talks, there's talks about fixed projection and perspective as a complementary concept to geometry at all. That the fixed projection and perspective provides the same kind of notions as the contents of Euclidean space and Cartesian space. But here it says with regards to Fraunhofer diffraction, which is Section 88 in general considerations. To answer this question, it is convenient to draw the wavefront R or R prime of a wave that has just left the lens. We may regard this as part of a spherical surface with center Z, radius equal to the focal length F. If we take O as origin and OZ as axis of Z, then the coordinates epsilon eta zeta of any point Q on the surface satisfy the equation that looks kind of a lot like the plane wave from the formulas we were talking about before. The parametric form of zeta squared plus this quantity. That was epsilon squared plus this quantity, zeta squared minus zeta minus f quantity squared equals f squared. And the epsilon squared plus zeta squared equals 2f zeta. So that also speaks and reflects on this, the having and doubling spaces. That because the mathematical formula has it, that the physical one does too, as far as it's attached. The image of a star in a telescope of long focal length. The star is so far away that it may be regarded as giving out a beam of parallel light. We have just shown, therefore, that the image of the star is not a point, but a pattern with maxima and minima, depending on the shape and size of the lens. For example, if a rectangular aperture bounded by eta equals plus minus a, zeta equals plus minus b, is placed immediately behind the lens L, the diffraction pattern is a grill network. So a grill network, I'll be curious to look this up now, as in Formula 36. And a circular aperture gives diffraction rings around Z. In any case, the finite extent of the central maximum zone will put limits on our power of resolving light from two close stars. So that gets into the theory of telescopes, the theory of optics, the theory of usually the geometric quality of light, that this fixed projection and perspective makes for that all such things are a matter of usually parallax and the stereoscopic, vis-a-vis what arrives at something that can be determined to have kind of its properties as would be a projection and perspective in 3 dimensions. That is kind of usual kind of thing. It's interesting. So that's there's some books here, and they're about multiple beam interferometry and stuff what gets into holograms, the technology of the holograms, technology of the laser, the technology of optics, the technology of photonics, what makes for that, because you don't really care if power goes over the line, but all you care is that an image does, that photonics offers a much lower power means to accomplish this with much less lossage over the course of it by the production of the photonic monomers that comprise fiber optic cable and their strands and wrapping and this and that. It makes it much more difficult to put one of those back together. Any break in a fiber optic cable is pretty much irreparable. It's not designed to suffer such a break, but otherwise it's a pretty great thing. Here's a telescope. I don't really have a reason for this to be sitting here, but what this is a cheapo telescope, and it's about 8 optical power, and it's got a little sight. The idea being you find kind of this section of the sky you're looking for, and then it's got some cheap lenses in it, and what it does is then it just it has a little stand, and then it just you can view the sky. Here it's in the city, so I don't have much of the sky to see because most all of the lights in the sky at night are satellites or the moon. That's all there is to it here in the city. Let's see then. Talked a little bit about waves, and here's the book on waves and layered media. So let's start with what this author Berkowski has decided to say. So the other day we looked at the table of contents of the first chapter of the wave book, and so we kind of got into about the rest of chapter 1 and a little bit of chapter 2 and then towards the end. And so here this chapter 1 says plane waves, so this is kind of what we're talking about, in discretely layered media. So as of layer 1, layer 2, layer 3. Plane waves in homogeneous, unbounded media. There's no difference in the constants of the propagation. It's a constant. Reflection of a plane sound wave from an interface. So this gets into the whole idea of the geometrical, where the angle of reflection is the opposite incident angle according to the angle of incidence for the wave, and the optical. That the optical adds up to be like so, kind of. With regards to Fresnel and that light kind of takes all paths and makes an image, then is for the particular properties of the light, like vis-a-vis, these are pretty much models of acoustic waves in water, and with regards to the design of boats and sonar and such things. Or it's the result of the studies where it's like so. Reflection from a plane layer and a system of layers. Here we get into the depth, is that the depth of under the plane is basically modeled as unboundedly deep, infinitely thick, an infinitely thick shell or something like that. Whereas with regards to layers. In the Mogan's book, The Nonlinear Electrical Mechanical Effects and Applications, a lot of reading was done, and it basically establishes those as with regards to Christoffel and stress and strain and the tensors and the conditions, and as to why the piezoelectric and the electrical mechanical. Thusly makes the surface acoustic wave transducer, which is a sort of a device which makes, after treatment in the terms, that it's possible to provide a value as an input over time to make what would otherwise be a non-tractable computation tractable. When you hear about quantum computing, sometimes what that is the idea that would actually have something after like the aspect type experiments, and that would actually be like, this is courtesy the properties of a quantum system at superposition and solving all the things at once and then collapsing to the answer. But otherwise, what it really means sometimes is like, we are going to take an FPGA, a field programmable gate array, and we just happen to have them nowadays so we can print them out in sheets however we so want. And we're going to just make it very wide, and we're going to give it behavior everywhere that's going to kind of flow like this surface acoustic wave transducer. And then it can solve some things. It's just like simulated annealing is just like another numerical method to arrive at an approximation for this. That it's not quantum computing, it's kind of just simulation of a quantum computing. So anyways, they've invented that since at least 40 or 50 years ago. And it's used today in what's wrapped as new and called something else. The surface acoustic wave transducer. So anyways, that was a lot of the learning from Mogan and the surrounds, and also particularly the daring of his application of these methods, and then the reasons why they get they are still as kind of underdefined as the Fourier style analysis when it was new. There are still formal questions and theories in the theories about how things and why they should be. And so uniqueness results of the day are distinctness results of later days. If you'll excuse me, sometimes when I say reflection or refraction, I'll say refraction or reflection. It's unconscious, but I notice it. So, free waves in plates. Reflection of a sound wave from a plate and the penetration of it through plate. Thin plate approximation. See, these I'm familiar with a lot of different terms and concepts. So in terms of having a massive glossary, it helps a lot because then you can relate all kinds of different things. Reading is fundamental, and spelling is particularly important, and etymology is the word. Well, let's see here. Wednesday afternoon or so. This is my lunch break, basically. I'm working on some code, and what it does is deal with the database file system, message queue, and web services on the nodes of the system. It's not on the cloud, though, but it is a distributed system on the network. Preface to second edition. A number of new problems have been treated in this second edition. These include the theory of a waveguide in a medium in which the wave propagation velocity c equals c of x, z depends on two coordinates, the theory of a surface waveguide and the waves of whispering galleries, including the case of a solid. Reference etalon equations and reference integrals, diffraction waves, etc. The exposition of other questions, such as the theory of caustics, for example, has been greatly expanded. On the other hand, part of the material pertaining to an underwater sound channel, which is not of general interest, have been excluded. This and similar problems are dealt with at much greater length in a special monograph on underwater acoustics, just completed by the author and his colleagues. The rest of the material has been compressed somewhat by virtue of contemporary methods of presentation. The bibliography has been increased considerably. The author expresses his deep gratitude to I.F. Chetenkova for highly valuable assistance in the preparation of the second edition. Elbrus. Preface to the first edition, in case we weren't missing anything. A systematic exposition of the theory of the propagation of elastic and electromagnetic waves in layered media is given in this monograph. A considerable part of the material originated with the author and has appeared earlier in a number of journal articles. I have endeavored to present the results of other authors in the spirit of my own as far as possible in order to avoid methodological disharmony. Furthermore, as one of my primary tasks, I have attempted to give the reader a clear physical picture of the phenomena under investigation. As regards the mathematical rigor, it is possible that it has not been sustained throughout to a sufficient degree in order to avoid making the presentation too cumbersome. Opportunity. The simultaneous presentation of the theory of propagation of elastic and of electromagnetic waves followed in the book is quite advantageous since the same mathematical methods may be applied in both cases. These are the models. Also, as a result of this simultaneous presentation, each region is enriched by the methods applied in the other. Thus, for example, the impedance method developed in acoustics and radio engineering may be quite successfully applied in calculations of multilayer reflection reduction of optical systems and interference filters. The bibliography given at the end of the book is fairly complete, but is far from exhaustive. And he thinks V.A. Polyanska and Treshtankova again were of great help in checking the equations and in preparing the manuscript for publication. So that's just kind of the tenor of this kind of work with regards to its significant applications in all these different fields, with regards to the models they share that are the same and the models they share that are different. Excuse me, I don't intend necessarily to sound too as sonorous or not, but it reflects where I'm from. So what I'm curious is to see if radar and sonar refers to this book. Not directly. Well, maybe perhaps this is as but for the appendix, because there's not very much to it, and there's a lot in this book. Moment in motion, the waveform. Here we have some more references, and as alphabetically, there's quite a few different papers in this book. So this for example, the previous one was about differential equations. This one is about boundary value problems and diffraction theory, scattering theory, electromagnetic signal propagation, sonar echo analysis, radar echo analysis. So one imagines that at any rate they would have been familiar with each other's work. Here, there's mentioned the far field approximation, the radar echo prediction problem. The analysis of this problem presented below closely parallels the analysis of sonar echo prediction. Thus, both pulse mode and carrier wave or continuous wave mode operation of radar systems are treated, and the construction of pulse mode echoes is derived from the theory of continuous wave mode echoes, CW continuous wave. Again, and then here, for example, these few pages of references, like Plancherel formula for non-unimodular locally compact groups, Calcul symbolique sur les opérateurs de Calderon-Zygmund, special functions in the theory of group representations, while Heisenberg wavelet expansions, sur certain groupe d'opérateurs unitaires, principe d'incertitude, ondelettes, fonctions splines, et analyse graduée. This is from the 80s, so it's pretty cool. It's the field. No Bukowski in this. So, that said, there's a lot going on and ongoing, and what I'll be looking to do is figure out how, with regards to electromagnetic wave, electromechanical effects and applications, waves and layered media, and radar and sonar, that they all form a continuous sort of milieu for moment and motion with regards to the models of and how it can be so applied the measures for these sorts developments. Well, it's a rainy, cold, dark day here. It's been a rainy, cold, dark day here. No, it hasn't been that bad. Yesterday was nice. Flip a coin. It'll give you a better guess. One of my favorite facts about the real numbers is that if you flip a coin, it starts to sample a real number. Its first or its most significant, the order of magnitude of its most significant fraction, and so on for each next. It's like 0.00000 or 0.11111 for 0 and 1 respectively. So to sample a real number, you basically can arrive at, for any given partition of the real numbers into equal portions, uniform. You can sample from uniform by flipping a coin enough times and finding where it lands in what bin, and it's rolled that value as of a die of a usual polyhedron with the right number of sides. So anyway, to sample a real number at all, you'd have to flip the coin infinitely many times. But each time you flip the coin, it not just refines the previous sample, it starts another sample. So doing, one sample of a real number is infinitely many samples of real numbers. Now, it's very, very unlikely, you might imagine, to arrive at that it would be 000 or 1111. It just wouldn't show up. According to combinatorial enumeration and combinatorial explosion, it just wouldn't show up. But if it did, it arrives at the weight of itself infinity many times. This helps explain why sampling numbers results in things that are rational. Hey, have a great day. We can hope. We can hope. And we can hope and that's about it. All right. Have a great day.